off and on through the periods yesterday. There we go. Now it's working. But there are 3 types of boundaries. What are they? When plates come together, there are 3 different things that the plates can do in retrospect to each other. I don't care if it's oceanic or continental. Form, you're right. Okay, so if they split, it's divergent. And that's what happens at the oceanic rifts, like the Mid-Atlantic Ridge. If it's convergent, if they converge, they come together. And lots of different things can happen depending on if it's oceanic, continental, or continental. But converge means that they come together, they collide. So what does transform do? They slide. Not this way. They slide on, I guess, what is that, the x-axis. Which of the 3 types is the San Andreas Fault? It's transformed. Now, transforms are most common down in the ocean. Obviously, there are some of them that are actually in continental crust, which is the San Andreas Fault, but it's nowhere near as common. Oh, my goodness, frozen. And then, like I said, we should get through this quickly while I'm on a dry run. I do need to teach you how to use the calculator to calculate how much. Well, first, what's the magnitude from the Richter scale? And then how do you calculate how much energy that actually translates into? It's really not difficult at all. If I wanted to, when I showed you those lines, the way that the S's and the P's actually travel through the Earth, there's a lot of calculus and geometry and trig that's involved, but we're not going to do that. Snell's law especially really is not that difficult. You need to know the differences between sine, cosine, and tangent. Is it opposite or adjacent or hypotenuse? That's SOHCAHTOA stuff, which I think they still use that acronym. But we're not gonna, maybe next year I'll do that. I'm not gonna worry about it this year. But we're specifically talking about earthquakes. Earthquakes can happen at all 3 types of boundaries. It could be oceanic or continental crust that's coming in contact with each other. I do have one student that he's just now starting at Earth Space, didn't have it last semester. I said, well, you're going to have a lot of fun. So when you have questions, please ask, because a lot of this stuff carried over from last semester. Continental crust is the continents. The igneous rock, the meter kicked on. The way that cools, because it was underground, it made granite. And granite is less dense than what happens with oceanic, which is technically outside of the Earth, which is basaltic, which is more dense. I know it's under the ocean, but it's not inside the crust itself. So continental is less dense. It's granitic. Oceanic is more dense. It's basaltic. It has to do with the elements themselves that make up the rocks. The heavier elements are going to make a more dense substance. There is one other one that we didn't really talk about yet. There are different types of oceanic crust. If it's older, it's going to be more dense. If it's younger, like at the ridges itself, it's going to be less dense. Less dense is still going to go up top, and the more dense is still going to go down underneath. That doesn't change. But we did not mention this particular type before the break. Answering the focus, essentially. Divergent, it splits. It moves away in opposite directions. This is what happens at the ridges and the rifts. This is what's happening to Iceland, and we will take a look at a documentary on Iceland. Yeah, the documentary will take the entire period. I don't think I'm even going to have an opener. It's just going to immediately start. I even had to put a special ad blocker on my computer so that the YouTube videos wouldn't pop up. And let's just hope that it doesn't get blocked out of YouTube because of copyright infringement, because it was like a Discovery Channel documentary. I didn't put it on the internet. I found it, so it's not my fault. Big as yank. But worst comes to worst, I can always get on my Prime account and I can play it that way. But the plates move away. The type of fault is called a normal fault. And with a normal fault, when you have this splitting, whenever the earthquake occurs with the fault, you have a piece of rock that breaks off from the original rock or the mother rock, and it's always going to fall down. That is a normal fault. It is a normal process, specifically from divergent boundaries, whether those be oceanic or continental. That's what happens. If it's a divergent plate compared to a convergent plate, yes, there's still earthquakes, and yes, there's still volcanoes, and yes, the lava is still going to kill you if you try to swim in it. But divergent are not as intense as convergent. There's more energy stored with the crashing together than there is a splitting apart. I said, don't go play in the volcano. Don't try to do it. I don't know, y'all. I get some weird questions in some of my classes. But at the bottom of the ocean, the Mid-Atlantic Ridge, which is the longest mountain range on the planet, that is what specifically split Pangea in half. You have all different kinds of seismic activity at the Mid-Atlantic Ridge. There's lots of transform, the side-by-sides. Like you see, I don't think I have it on the screen, but when you take a look at the ridge, which isn't perfectly straight, going from north to south pole, but you see these little sideways cracks. Those are transformors. And yes, there are other ridges. It's just this is the one that we talk about the most. It is pushing the western hemisphere to the west and the eastern hemisphere to the east. It's about to get really warm in here when that heater finally really kicks on. All right, so convergent, they come together. They crash into each other. The type of fault here is called a reverse fault. Oh, a normal fault is a tension fault. A reverse fault is a compression fault. It just means to squeeze together. And with these, instead of the piece of rock that falls off falling, it actually gets pushed up. It does the opposite of what a normal fault does. This is more of a review from before the break. Oceanic will always go underneath or subduct below continental, and therefore will push the continental up even more, which is why you see mountain ranges along coasts of continents, like the Andes in South America, and the Rockies, and the Cascades that go up through Washington, where St. Helen is. Geography is not my strong point. I think they're called the Cascades. I'll have to go back and double check. Volcanoes happen all the time here. We call this the ring of fire off the Pacific plate. All the way up our west coast. It goes up around, comes around the other side, all the way down to Japan. The Hawaiian Islands that are smack dab in the middle of the Pacific plate is not from a subduction zone, that is from a hot spot. And we mentioned those yesterday. Hawaiian Islands are like that. Canary Islands are like that. There's a couple other little blips in the middle of the plates. I do not know all the names of all the different volcanic chains. I just don't. I said older oceanic is more dense. If you have two oceanic plates that come together and make a really, really, really deep trench, like the Marianas Trench, the older is going down underneath the younger. And then continental, there is nowhere for them to go except up, and that is how we have mountain ranges go, like the Himalayas, the Rockies. I think we do landforms tomorrow, things like plateaus and plains, and you probably know some of the phrases that we're going to talk about, maybe not in depth. If that's not tomorrow, it's Monday. To transform, the third major type. These are the ones where they slip past each other. This is what happens with the Juan de Fuca plate, which is off of the west coast of the United States, and the North American plate. The Juan de Fuca plate is tiny. It's itty bitty, but it's trapped between the Pacific plate and the North American plate. And instead of going underneath, it slips up the west coast of California. Eventually, San Francisco and Los Angeles will be next to each other because one of those cities is on the Fuga plate and the other one is actually on the North American plate. And no, California is not going to break off into the ocean. It's slipping. It's the left-hand side towards the ocean is actually moving north. Now, there are thousands of earthquakes every day. Most of them are so tiny we can't feel them. The seismographs can pick them up. It has to be around the 2.5 to start making light swing. But if you're outside, you normally don't feel those. You can see them if something's suspended and it moves. The stronger ones, M stands for magnitude. That is the unit for earthquake, for seismic waves. The capital M stands for. Strong earthquakes are around a magnitude of 7. They have, not necessarily in our country, but they happen every day. The bigger ones that are more than a magnitude 8, they're nowhere near as common. Because I will teach you how to analyze. Like if we know the magnitudes of 2 different earthquakes, how much more energy one has than the other. Let me double check on mine again really quick. What did I put? Here it is. I'm missing some people. Ooh, it's getting toasty. Oh, there's a lot. That one. Joseph, Caden, Natalie, I got you now. Still don't see Colton. So Jimmy, Dylan, Cameron, Kale, Erica, Sarah. I don't see Sarah. I don't see Caitlin. Okay, I think I got everybody now. Okay. Please. I don't know if I put this as a question or a bullet on the skeleton for your notes, but this is an image of the different depths of earthquakes that are happening, and so obviously you probably can't see me pointing at the board. So here's the Pacific Plate. And you notice that there's a heck of a lot of activity all along the edges of all of the plates for that matter, but it's really, really interesting right here because you see all of this blue. I know you guys can't read it from there, but the orangish looking ones, those are very shallow quakes. They're not very deep. They're happening more towards the surface of the planet. The M would be a mid-depth earthquake, so deeper, but these blue ones, these are the extremely deep earthquakes. So the deepest quakes, these are subduction zones where the oceanic, which is the Pacific plate, is going, this is the Eurasian plate, this is the North American plate, the Nazca plate. Where you have subduction, that's where you see these deep quakes. Where do you think the most common places you're going to find a volcano? The Ring of Fire, where you see these blue letters, those are your deepest quakes. So they're further down towards the mantle, and it's when those have its epicenter is up at the surface. Deep down is called a focus. When the focus occurs very deep in the earth, it has a much higher chance of actually penetrating the crust all the way down into the mantle, and then allows that volcanic magma to be able to come up. And eventually, once it shoots through the crust, it's now lava. Yes, there are other volcanoes here, okay, but most of our volcanic activity does actually occur right around this part of the Ring of Fire. So the actual thing that causes the earthquake, where you have stored up energy that just can't take it anymore, and something occurs to the rock. It slips, it cracks. We call these faults. Where the earthquake occurs within the earth, not on the surface, within the earth, is called a focus. Now, if you go directly up, like just straight up against the pull of gravity, where that is on the surface, that's called the epicenter. That's the word that you're probably familiar with. And so what this image shows you is down here on the fault, This is the fault, where the actual energy finally is released. That's the focus down here. It's going to spread out in every direction as at the same speed. P waves move faster, S waves are going to be a little slower. P waves are around 8 kilometers per second, S is about 4.5 kilometers per second. But directly above that, that's what we call an epicenter. And we can pinpoint where those are using seismographs, but we need at least 3 of them. That is called triangulation. It's the same thing that happens with this. And like I said before, throwing your phone on airplane mode, they're still going to be able to see you. Trust me. These things track you. What you have to do is go to a website and open up something on social media, and it's amazing how all of a sudden ads for that just pops up. A person who studies earthquakes is called a seismologist. Okay, their tool to measure earthquakes, how strong they are, called seismographs. And when your fault all of a sudden does its thing and creates a focus, whatever it is that occurs within the earth, that energy travels out. Some of it goes up to the surface. SNPs do that. Some of it actually goes down and tries to go to the other side of the earth. S's cannot do that, only P's can. But these seismic waves are picked up by these seismographs, which looks like a drum, got a piece of paper on it, and the drum is slowly rolling. And then when all of a sudden you have the vibration of the quake, that needle moves back and forth, and the stronger the vibrations, the more animated the amplitude of that wave is. You have at least 3 different seismographs that analyze the speed in which a P and an S wave arrives at a station, and they can pinpoint exactly where that epicenter is. Technically, the S wave and the P wave, as long as they stay within the earth, don't cause damage. It's when they hit the surface and the S and the P waves combine into something called a surface wave, which there are 2 major types, and we'll get to in a second. That's what causes the destruction. The interior of our Earth, the outer core, actually completely absorbs S waves. And that term that we talked about was called attenuation. S waves cannot go through a liquid, they can only go through a solid. S waves can only match the boundary of the outer core because it can't go into the outer core. P waves are the ones that are used according to their speed and their refraction, which is Snell's law, is what tells us how thick the outer core is and how thick the inner core is. What makes the focus occur is called stress. Rock can only take so much stress, and it is going to give. It can take quite a bit of energy, but it's still going to hit a breaking point, no pun intended. It's going to hit a breaking point where it can't absorb that stress anymore, and something is going to give. This was from the 1906, once again, 8.3 magnitude. That's what the M stands for in San Francisco. This fence used to be on a straight line. It got shifted about 10 feet over, like immediately. Then they had to come back in and they had to patch it over here. I didn't have to do all the grade changes and ate up my morning this morning. I'll go back and see if I can't find the image of the bridge that gets torn apart by the quake. It's in black and white. It's older. It's before we understand these seismic waves. Man, this bridge, it's a suspension bridge. It is literally doing this. And there are people and cars on it. Not the Golden Gate Bridge. The bridge I'm talking about was destroyed in the quake. You know, like I said, it's not that people were stupid. They didn't understand. Things have a natural resonating frequency. And whoever built that suspension bridge, it just so happened to be the frequency of the magnitude quake that hit it, and it got demolished by it. And I'm sure people died. I mean, they were on this, literally, it was billowing like this. I'll see if I can't find it. If we have time. There is video of it. Actually, I don't think you could even hear sound in it. I mean, it was an older quake. The actual earthquake, before it strikes the surface, the big quake, the main quake, sometimes you get warning, and those are called foreshocks. It's before the main earthquake. Most of you have not heard that phrase. What you've heard is aftershock. So once the big quake happens, whatever its magnitude is, you get little ripples behind it as the earth is settling. So like I said, you have massive amounts of energy that are released, and that's your main quake. And then the earth sort of, not normally nowhere near as high, it settles back into place, and those are aftershocks. They can cause landslides, mudslides, same thing. Landslides. It can all of a sudden create a volcanic vent that sprays magma everywhere. It can cause tsunamis. The ones that happen out in the ocean, the one that happened off the coast of Chile in 1964 or 65, that thing sent out a tsunami that was 100 feet tall, and it almost took out everything on the main island of Hawaii. Okay, so Chile, Hawaii is way out in the middle of the plate. In fact, that wave reached all the way to Japan.
So it was like the biggest tsunami alive to underwater.
I'm not sure how high the water was with the one that hit, it was the day after Christmas in like 2005. And it was like, it wasn't Tahiti, but it was one of those Polynesian islands. And everybody was out celebrating Christmas, like the tourists are out on the beach. And I'm sure I've mentioned this before. If you're on the beach, you're not going to feel the tsunami coming and you're not going to see it until it's too late. All of a sudden, it looks like the water gets sucked into the ocean, not a tide. Like, there's no more ocean. Run, run, go up, not in a tree, go up in preferably like a hotel that's built really, really, really well. Yes.
Like, not in the case of a tsunami, of course, but I feel like the best thing you can do in an earthquake is to go outside.
Get outside. Get away from buildings.
Okay, because it doesn't really make sense to be inside.
Well, the problem is a lot of times you don't get that much advance warning, and you're not going to have time, especially if you're like in an apartment complex and you're like way up, to be able to get down and get out. But if you do have the ability to get outside, out in the open, away from stuff, that would probably be the safest place for you to be in an earthquake. As long as the ground doesn't open up beneath you and swallow you whole. But that's, I don't know. I don't, California is beautiful, but
Yeah, like
I
I
don't
said,
know.
I guess that place is just a disaster.
Every area has something. Whether it be Tornado Alley, it be hurricanes, it be wildfires, it be earthquakes. There's something somewhere, no matter where you live.
Yeah.
So, and then in the last case here, sometimes you do have a whole new island mass, like in the case of Hawaii and the Canary Islands, that are created when you have massive earthquakes. Okay, I remember this one, y'all. I was 11 years old when this happened. This was the one that happened in 1989 in San Francisco. And the only reason, y'all, I laughed, not because I necessarily thought it was funny, but just it was so ironic. So these bridges, these overpasses, these people, I don't know how they got those off of there. They're trapped. But because you have gaps with these faults that are completely gone on both sides of the actual bridge. I can only imagine what was going on in these people's minds when the road started moving. So I remember everybody kept saying, is the big one gonna happen after this? Is the 10 gonna happen after this? That was a 7.2 magnitude. It destroyed a whole bunch of stuff. This was the quake that really changed the building codes in California because it damaged so much stuff. Minor earthquakes. They only last a few seconds. So you don't really have like the time to get outside if it's just a minor quake because it's over pretty much as soon as it starts. Major earthquakes around a 7 up, depending on how high it is, are going to last for somewhere between probably 10 seconds to a minute. That one that I just showed you the picture of that tore the bridge apart, or the overpass apart, that was a 15-second quake. So it's not like they're going on for an hour. It's a very quick release of energy, which is why earthquakes are so damaging. The one that split that fence that I showed you the picture of, that one was 40 seconds. That was an 8.3. Hopefully you're noticing a trend right now with the magnitude and how long they're lasting. And then the one that was in Alaska, that was a 9.2, that thing lasted for 3 minutes. So what's the trend? What are you noticing with magnitude and how long they last? Yep. The larger the number or the stronger the quake, the longer it's going to last, because it's that much more energy that's having to be dissipated in the earth itself. And I hear people go, that's only 0.9 higher. Well, I'm going to show you how to calculate energy, because this is a logarithmic scale. We have had some that were stronger than that. The one in 65, the 9.5 that happened off of the coast of South America, that one did lots of destruction way on the other side of the Pacific Ocean with that tsunami. Like I said, the tsunami was like 90 or 100 feet tall. It was huge. But you don't notice the tsunami when you're out in the ocean. The tsunami doesn't build in height until it gets closer to the shore or the beach, whatever. I'm from the Northeast, so it's the shore. So as the water is traveling, so here's the beach, here's the shore, and then we have a deep drop off. So let's say the earthquake happens somewhere over here, and you have a large piece of rock that breaks off, falls down, and it pushes the energy of the water this way. On the surface, this is the water. Because the ocean is so deep that it's traveling for a while, all you see is what we call a swell that is traveling until it hits where the continental shelf is, which has a very steep increase in elevation, which is going to make that wave even higher. It's still going. And then when you get much closer to the beach, I hope most of you have been to the ocean, you can actually go out for a decent distance, and sometimes there's sandbars. But here, this is what actually makes that tsunami. And you have the little people over here, they're going, oh, trying to run away. But you can't outrun a tsunami, y'all. They can go over 600 miles an hour. My beautiful artist rendition of what happens underneath the water with tsunamis. But if you're way out here, like on a boat, you're gonna be like, these are weird little waves that we experience, but it's not like a rogue wave that would capsize the boat itself. All right, picking up from yesterday. P waves. They go through the crust, both the continental and the oceanic, and then the asthenosphere, and they can travel through the mantle. These are pressure waves. They are longitudinal, which means it looks like a pulse. They still go in equal directions out from the focus. So it's not just in a straight line, but it's three-dimensionally, every which way. They are the fastest of all of the waves, and they travel at approximately 8 kilometers per second. This is the first one that gets picked up with a seismograph. Primary wave, P wave, primary wave. It's also called a pressure wave. So both solid and liquid. Once again, P waves are the ones that map how thick the outer and the inner core are, and the speed at which they travel through them lets us know that the outer is liquid and the inner is solid. Like I said, we're not gonna do the heavy math with this, because it takes a few levels of calculus to do it the right way, and y'all, I don't like calculus. Nice. Let's see here. Let me make sure that there's not another one on here. Yes, there is. There's one more on here. So back and forth. So in a pressure wave, it's not this motion. Okay, that's called transverse. In a pressure wave, it goes, well, I've got all this stuff on my desk. I really tried to clean it up. I really do a good job. They go, you can see like the compression that goes back and forth. That is what a longitudinal wave is. That's how my voice is literally banging on your eardrum. It's because it's a pulse like this. And then your brain decodes those pressure waves as sound, and we understand speech. If you would have taken physics, you would have known the difference between longitudinal and transverse before, but most of you haven't. All right, S waves. They travel through the crust, okay, the outer layer, which is the both continental and oceanics, and then the mantle itself. They're the second ones to arrive at a seismograph because they're slower than P waves. They move at about 4.5 kilometers per second. S waves are also called shear waves. They are transverse waves, and the energy moves perpendicular to the application force. I'm very much going back to my physics language right now because I understand how waves move. They cannot go through liquid. They can only go through solid, which is why the shadow of an S wave is so large on the other side of the planet from where the epicenter is. It can't go through the middle of the Earth. And there is one more here. So, S waves, waves are so great at showing waves. So if I'm moving this side and the energy is going this way, it's moving up and down. The energy is trying to go from you guys, from your left to your right, or from my right to my left. But the actual wave itself is moving up and down. That's what moving at right angles or perpendicular to the application force, which is what this means. A sine wave or a cosine wave. When these two hit the surface, this is surface wave. This is what causes the ground to shake. And they're either going to make the rock move side to side, like this, or it's going to make it move up and down, like this, depending on which one is doing more of a break at the surface, if you will. I don't think there's one more on here. Yes, there is. This is what releases the energy of the earthquake at the surface of the Earth. This is what causes the damage to the buildings. Like I said, places like California that experience earthquakes all the time, they have different codes for their buildings that have to be used. Their buildings are meant to sway more than ours are. We don't get massive earthquakes here. We do get earthquakes in Texas. It's just not like the ones from the San Andreas Fault. All right, two major types of surface waves. They are called Rayleigh and love waves. Both surface waves. Love waves are slightly faster than Rayleigh waves. Love waves go like side to side like this, like a snake. And then Rayleigh waves go like this. It has a rolling motion. It's just like the waves on the ocean. Now, it is a combination of both longitudinal and transverse. But Rayleigh waves do this, like an ocean surface, and love waves do this, like a snake slithering across the ground. It's still both. It's the P, which is making it move forward in a pulse, and then it's that right angle. It's just, is it doing it on the y-axis, which is a Rayleigh, or is it doing it on the x-axis, which is a love? They're both damaging. Love waves tend to do more damage than Rayleigh waves do, but they're both destructive. Oh no, I have to teach you how to do two more. I have to teach you how to use the information from the Richter scale. This is, when I taught physics, this is the one type of wave that I didn't really ever go into. But I understand the mechanics behind it because I understand how transverse and longitudinal waves work. Seismic waves are a combination of the two. And I always used to tell that to my physics kids, but I was like, I've never been educated on earthquakes, but I understand what's actually going on within the earth, understanding the two major types of waves. All right, how to use the Richter scale. The Richter scale goes from 1 to 10. If you have an increase of 1, so if you go from a magnitude 1 to a magnitude 2, a magnitude 2, like a 2.0, is 10 times stronger than a magnitude 1. It is on a logarithmic scale, 10 to a power. It's not, please don't freak out, because I normally don't make you guys do math. You guys have this on your thing. We're going to figure out how much bigger an 8.7 magnitude is than a 5.8 magnitude. This is how you do it. You take your two magnitudes and you subtract them. You take the larger wave, which is a 10 to the 8.7, and you divide it by the smaller wave, which is a 10 to the 5.8. When you divide exponents, you subtract them. When you multiply powers, you add them. I know you guys have had this in your math class, but you may not have done it for a while. So we're going to do 8.7 minus 5.8. And when we do this power, it tells us how much larger that wave is. So an 8.7 magnitude is 794 times more impressive than that of a 5.8. We're going to take the information from here to figure out the energy. The difference of these times 1.5 and then 10 raised to that power is going to tell you how much energy in joules that actual earthquake occurs. How much more energy is present in that 8.7 than a 5.8. So 8.7 minus 5.8 times 1.5 is 4.35. Don't take me in the calculator if you want to. 10 to that power means that an 8.7 magnitude earthquake it would take 22,387 5.8 magnitude earthquakes to equal one 8.7 magnitude earthquake. That's how much more powerful it is. This is the only thing that I'm going to ask you to do. And I think there is one like this on the assignment that's today. I think it's the last one. So, what's the difference between these? My math, y'all, I haven't had enough coffee. 8.7 minus 5.8. There is a difference of a 2.9 magnitude between these two earthquakes. It does not sound like much. But like I said, it's over 22,000 times more energy in that one quake than the other. So the magnitude 10 quake would be catastrophic, would probably affect Earth's orbit. Like, I wouldn't want to be exposed to a magnitude 10. The Richter scale does not go beyond a magnitude 10. There's one more slide. You guys have this on your paper. This is the Mercalli scale on the left-hand side, and then the Richter scale on the right-hand side. And I just put this on here in case you were curious as to what magnitude, because we use the Richter scale in the United States, what would occur damaging-wise. Like a magnitude 7, most masonry, which means brickwork, and frame structures are destroyed, the ground is cracked, rails are bent, and there's landslides. Category, or a magnitude 8, total damage. Waves are seen on the ground surface, lines of sight and levels distorted, and objects are thrown up into the air. It's an 8, not a 10. The strongest recorded earthquake with the seismograph was the one that was off of Chile that I keep talking about that sent the tsunami all the way across the Pacific Ocean. I don't know how many people it injured, but it killed almost 1,700 people. The largest node in history, we didn't have a Richter scale in 1556. Killed almost 1 million people in China. So these things can be extremely destructive. Like I said, I mean, California is pretty. The weather is beautiful.
What's the highest in the history? 10?
The highest on the Richter scale is a 10.
So if it's It's never gotten to that highest value.
The highest that we've recorded, and I double checked it, because I'm constantly fact checking myself, because now, things change. That's the highest recorded. We don't know how powerful this one was. But then again, you go back into the 16th century and they were probably all wooden houses. They didn't have the infrastructure that we have now. But I wouldn't want to be in category 10. I would not. I need to double check my QDOs online. Okay,
I remember, I don't know when it was, the tsunami in China, not the one time, but like an earthquake way on the ocean called like a huge tsunami.
So that's what this one did. It was just a while ago. Okay, so I went over what people still had not turned in. If you have not done the assignment from Tuesday, I keep saying Monday, I mean Tuesday, do that. If you're caught up, work on this one. And tomorrow we are doing, I'm going to say it's not topographical maps. Tomorrow is landforms. It's tomorrow's. And if you know you're not going to be here, like I said, everything will be in Canvas. Everything is already in Canvas. I just don't think you can access the assignment until it's opened up on the right day. Let me stop presenting.